Okay, guys, so this is a joint exploration with Professor Pedro Reutemann out of University of Brasilia. Let's look at 5 periodics, or n periodics in general, in the elliptic billiard, shown black here. This is the elliptic billiard. The 5 periodic family, which I can animate, is shown blue. And the confocal caustic is shown brown. Now, let's consider the following construction. I'm going to draw lines from one of the two foci without loss of generality, F1, the left one. I'm going to draw spokes from the focus to each one of the vertices. Okay, and that's going to define n triangles. N triangles that together tessellate the 5 periodic. So let's watch these animated. There are the 5 triangles. Now, since these are triangles, let's, for example, draw their incircles. Let's draw their incircles, and let's watch the 5 incircles. Now, each one of these incircles has a variable inradius. So, for example, let's sum those 5 inradius, and let's see if there's something interesting there. No, that sum is variable. Okay, very good. Now, let's do a similar construction, but instead of the incircles, I'm going to draw the circumcircles of each one of these 5 triangles in this case. So let's draw the 5 circumcircles. Here they are, and I can watch them. These purple dots represent their circumcenters. And since there are 5 circles, they all pass through the focus in this case, I can also compute their 5 radii, and I can sum those 5 radii. I can report them here. And as the simulation shows, the sum of these 5 radii is also variable. Now, here's the claim. Let's draw both constructions together. The claim is the ratio of the sum of circumradii by the sum of inradii is invariant for any n. So 3 periodic, 4 periodic, 5 periodic. So here we see that ratio being invariant for n equals 5. Let's repeat this construction for n equals 6, for example. Is n equals 6. I get invariant sum of circumradii divided by the sum of inradii. Let's do n equals 4, for example, in which case the n periodics are a family of parallelograms. I also get stable ratio of sum of circumradii by sum of inradii. Let's go for the n equals 3 case, and let's change this a over b a little bit, and let's watch that. I'm also getting stable ratio. So that's it. If any one of you that is watching this video might know of a technique to prove this interesting and intriguing result, do let us know. Thank you very much.